This example is a ladder example, or a right triangle one, where we have a ladder leaning against a wall, a 13-foot ladder. Make note that that 13 feet never changes. It's always 13 feet long. The top of the ladder slips down the wall at a rate of 2 feet per second. How fast will the foot be moving away from the wall when the top is 5 feet above the ground? So that's part A. And then part B is we want to know the rate at which angle theta between the ladder and the ground is changing. So we have our ladder, which is constantly 13 feet. So that's key. It's leaning against a wall. The top of the ladder, so this point right here, is slipping down at a rate of 2, so I'm going to put a little negative in there, feet per second. So then we want to know how fast will the foot be moving away. I want to know how fast this point is moving in that direction when we are 5 feet above the ground. So let's name some sides of our triangle. I named this guy X, I named this guy Y. So dx dt is equal to -2 feet per second. I'm looking for dy dt when x equals 5. Okay, so what you want to keep in mind, we now need to write an equation involving x, y, and 13. Well, hopefully you guys realize it's a right triangle. That's why our Pythagorean theorem is so helpful to us. So x squared plus y squared is equal to 13 squared. Okay, so now we need to take the derivative of this. So 2x dx dt plus 2y dy dt, derivative of 13 is 0. If I divide everything by 2, really I have x dx dt plus y dy dt equals 0. Now plug in. We know dx dt is 2 feet per second. I don't know what x is. We'll talk about that in a minute. Dx dt is -2. We don't know what y is, but we're looking for dy dt. We know we want to find dy dt when x is equal to 5 at that instant. So I plug in 5. Okay, how do I find y? Well, at that instant, when x is equal to 5, so when x is equal to 5, our hypotenuse is 13, we have a right triangle, and convenient that it's a Pythagorean theorem, so y is going to equal 12. It's a Pythagorean triple, I should say. Or you could use your Pythagorean theorem to solve. So solving that, we get -10 is equal plus, I should say, 12 dy dt equals 0. So dy dt, simplifying, is equal to 5/6, and let's get some units, feet per second. Now part B, at what rate is angle theta between the ladder and the ground? So right here, I want to know how that theta is changing. Okay, so set up an equation involving theta. And I recommend that you use one of your trig functions that involves the hypotenuse. I think our book uses tangent, but that gets a little hairy with our derivative. So I'm going to use sine. The sine of theta is equal to x over 13. Opposite over hypotenuse. So really I have 13 sine theta equals x. Now take your derivative with respect to t. 13 times the cosine of theta times by d theta dt, which is what I'm looking for, equals dx dt. Well, 13, the cosine of theta at this instant comes from that blue right triangle. 12 over 13 d theta dt is what I'm looking for. Dx dt was moving at 2 feet per second, but it was negative. Okay, some algebra, the 13s cancel. So we have 12 d theta dt equals negative 2. So then d theta dt is going to equal negative 1/6. Now we need to think about units. Theta in calculus, remember, is radians per unit of time we get from the word problem, seconds.